In this video, we're going to talk about discontinuity. So we're going to first determine the discontinuity at the given point, and then identify it as infinite, jump, or removable. An infinite discontinuity occurs when a function increases or decreases indefinitely at the given point. For example, if we have f of x equals 1 over x squared, we're going to evaluate at the given point x equals 0. So start by plugging in 0 into your function. So f of 0 equals 1 over 0 squared, which simplifies to 1 over 0, which is undefined. And because this is undefined, it means that we have a discontinuity in our function at x equals 0. So let's determine what kind of discontinuity it is by making an x and f of x table. We'll see what the function is doing on the left and the right sides as it approaches 0. So I picked two values to the left and two values to the right that are very close to 0. So when you plug negative 0.01 into the function, you get 1 times 10 to the 4th. Negative 0.001 is 1 times 10 to the 6th. We know 0 is our undefined, 0.001 is 1 times 10 to the 6th, and 0.01 is 1 times 10 to the 4th. So we can see on the left and the right sides we're getting larger and larger into a very large number towards infinity. If we look at our graph, that will confirm that. The graph of this function looks like this. We can see right here on the left and the right, x equals 0, both sides of the function are going towards infinity. And this was confirmed by our table. So this must be an infinite discontinuity at x equals 0. Jump discontinuity occurs at the given point for the function when on the left and the right sides there are two distinct values. For example, if we have f of x equals x squared minus 1 if x is greater than negative 2, and x minus 5 if x is less than or equal to negative 2. And we're evaluating at the given point x equals negative 2. So plug in negative 2 to both parts of the function. So f of negative 2 for the top function would be negative 2 squared minus 1, which is 4 minus 1, which simplifies to 3. F of negative 2 to the bottom equation is negative 2 minus 5, which simplifies to negative 7. So you can see on the left and the right side we're approaching two distinct values, so we would think this is a jump discontinuity. But let's prove this ourselves using a table. So I did the same thing. We're evaluating at that given point negative 2, and so we chose two values to the left and two values to the right that are very close. A negative 2.1 will be plugged into the x minus 5 equation because x is less than or equal to negative 2, and that gives us negative 7.1. And for negative 2.01 we will do the same thing and get negative 7.01. Then we have a negative 2, which was where we have the two distinct values. Negative 1.99 will be plugged into our top equation, x squared minus 1, because x is greater than negative 2. And that gives us a positive 2.96. And negative 1.9 gives us 2.61. So we can see on the left side we are approaching that negative 7 value, and on the right side we're approaching 3. So we have to have a jump discontinuity because we're approaching two distinct values. Let's also check by graphing. So a rough sketch of the graph will look like this. And we can see this large break or jump in our function. So this is a jump discontinuity at the point x equals negative 2. A removable discontinuity occurs when the function is continuous except for a hole at the given point. For example, if we have f of x equals x plus 3 over x squared minus 9, and we evaluate at x equals negative 3 and x equals 3. So let's start by plugging in our two given points. So f of negative 3 will be negative 3 plus 3 over negative 3 squared minus 9. And when you simplify, you get a 0 over 0, which is undefined. So we know our function is not continuous at negative 3. F of 3 is 3 plus 3 over 3 squared minus 9. which is 6 over 0, which is also undefined because there's that 0 in the denominator again. So at both negative 3 and 3, the function is undefined. So let's use two separate x and f of x tables to see what's happening at both of these points. So for negative 3, the negative 3.01 will give us a negative 0.166. Negative 3.001 is negative 0.167. Negative 3 is an undefined value. Negative 2.99 is negative 0.167. And negative 2.99 is negative 0.167. So we can see the left and the right side are both approaching this negative 1.67 value at negative 3, which must mean that that is the value that should be at negative 3, but because it's discontinuous, there must be a hole, because the rest of the function is continuous except for at that hole. So there's going to be a hole for negative 3, so this is a removable at negative 3, and we would see that it's going to be for x equals negative 3 will be a hole for negative 0.167, or negative 1/6 is the equivalent. So let's also do a table for 3. So 2.99 is negative 100. 2.999 is negative 1,000. 3's are undefined. 3.001 is 1,000, and 3.01 is 100. So we can see that we're going in two different directions from the left and the right as we approach 3. So this must be an infinite discontinuity at 3. So when we draw our graph, we will have something that looks like this. Their hole at negative 3, and continuing on.